Have you heard of CAN before? If not, then you are missing out an exciting new class of neural network that could revolutionize deep learning application. So today we will understand what CANs are, how do they work, and will showcase some real world applications of this CAN. So stay tuned. Now, first of all, what is CAN? Basically, this CAN is a type of machine learning model which is inspired by a mathematical concept called the Kolmogorov-Arnold representation theorem. So, unlike this traditional multi-layer perceptron, which have fixed activation function on each node, can replace these fixed function with learnable activation function on each edge or the connection between the nodes. That is, each weight parameter in a CAN is represented by a flexible function which is called spline rather than a single number. Now this allows CAN to capture more complex relations between the input and outputs compared to multi-layer perceptron, which results in higher accuracy and easier interpretation of the results. So additionally, CANs have faster scaling laws compared to multi-layer perceptron, which make them more efficient for certain type of problems. So overall, this can offer a compelling alternative to multi-layer perceptron with various benefits ranging from scientific research to industrial processes. So to understand CAN better, imagine you are trying to figure out how long it takes for water to boil given different temperatures. So when a traditional multi-layer perceptron might represent time as a linearly increasing function of temperature, but sometimes that's not quite right because there are non-linearities involved, and that is where this CANs come in. So instead of having one fixed function that applies everywhere, CANs let you define your own special function for each connection between the nodes in the network. So you could say the relation between the time and temperature looks more like a curve or a wave instead of just a straight line. Now this gives CAN a lot more flexibility and expressiveness, which allows them to fit more complex patterns and relations in the data. And since CAN don't need as many parameters as regular multi-layer perceptrons required to do the same job, they can often be trained more efficiently too. So this CAN, they work on Kolmogorov-Arnold representation theorem. So basically this theorem is a math concept that suggests that almost any multivariable function can be simplified into a combination of basic single variable functions which are linked through simple addition operation. For instance, imagine trying to calculate the volume of complex three-dimensional object made up of multiple shapes. So instead of figuring out the exact formula for each individual shape, you could break down the overall function into simple parts. Then you would add these simple components together to approximate the final answer. So by applying this approach repeatedly, you could gradually reduce the complexity until you arrive at a set of easier calculations which involve just one variable. So essentially this technique allows us to solve bigger problems using smaller building blocks, much like constructing intricate structures using Legos instead of starting from scratch. So it opens a possibility for improving various domains including mathematics, physics, engineering, finance, computer graphics, and even artificial intelligence, where dealing with high dimensions is commonplace. So what's the architecture of this CAN? So basically this CAN, also known as spline neural network, consists of three main components. First is the input node, then we have some hidden splines, and then have an output node. So instead of using fixed activation function like other types of neural networks such as multi-layer perceptron, can replace this weight parameters with flexible 1D functions, which is called splines that sit along connections or edges between the nodes. And these splines allow CAN to learn complex relations between input and output, especially when dealing with compositionality. So the input node receives the raw input data, pass it on to the hidden splines, which are essentially curved lines drawn through the set of points. And this each point represents a weight parameter, and the curve passing through these points is learned during training. Now this hidden splines allow CAN to capture higher order derivatives without introducing additional network layers or parameters, which improve its accuracy in certain cases. So this output node simply calculate a weighted sum of all the activations which are coming from hidden splines and return the result. So unlike most neural network, the scans do not require any non-linearity in their nodes. Rather, they operate linearly, which allow for easier interpretation and understanding of the model's behavior. So moreover, because scan can deal with compositionality, they can identify patterns within the structured input, which leads to significantly better prediction than traditional multi-layer perceptron when working with complex databases. So what should be the factors to consider when we decide whether to use scan or multi-layer perceptron? The first is interpretability versus accuracy. So if interpretability is important and accuracy is second concern, then can be a good choice due to their explicit representation of function. On the other hand, if accuracy is the primary goal and interpretability is less critical, then multi-layer perceptron might be preferable due to faster training times. Then comes data sizes and computational resources. So for small data set with limited computational resources, CAN's lower memory footprint and better numerical stability could provide advantages over multi-layer perceptron. Conversely, for larger data set and more powerful hardware, multi-layer perceptron's ability to process batches efficiently may outweigh these benefits. Then we have some grouping activation function. So to improve efficiency, CAN allows for grouping activation function into multiple heads, sharing the same activation function within each head. And this strategy can reduce the training time while still providing flexibility in terms of the type of activation function used. Then combining CAN and multi-layer perceptron. So hybrid approach combining elements of CAN and multi-layer perceptron could potentially offer the best of both worlds. So by leveraging the strength of both approaches such as CAN's interpretability and MLP's efficient batch processing, it may be possible to achieve higher performance and better interpretability overall. Then it has adaptability. So by introducing adaptability into the CAN, such as multi-level training or domain-specific basis function, it may be possible to further improve the effectiveness and efficiency for certain applications, particularly those related to physics and scientific community. Then there are certain advantages of CAN, like enhanced interpretability by representing individual neurons as geometrical entities, lower computational cost because of sparseness, and the capability to precisely replicate any continuous function by modifying specific hyperparameters. So by implementing techniques such as residual activation function, initialization scales, and dynamic updates to spline gates can address challenges posed by splines being limited to restricted domain. So when compared to multi-layer perceptron, although CAN may have several more parameters initially, so they often need significantly fewer owing to superior generalization capability and easier interpretation. Then comes the application of CAN. So this CAN is a type of neural network that combines the benefits of multi-layer perceptron and splines. So unlike multi-layer perceptron, CAN don't have any linear weight metrics and instead replace weight parameters with flexible 1D functions, which is called splines. And these splines help CAN to learn complex relations between input and output, especially when dealing with compositionality where the output is made up of simple parts. So in industry, CAN could provide significant advantages compared to traditional multi-layer perceptron. So one area where CAN might excel is in predicting material properties based on atomic arrangements. So traditionally, computational chemistry has relied heavily on density functional theory calculations to estimate materials' behavior at various conditions. Now, this density functional theory requires expensive computer simulations, which makes it impractical for some industries like drug discovery or semiconductor manufacturing. But with CANs, researchers may be able to predict how atoms interact with one another and how those interactions affect overall properties. So since CAN can handle compositionality, they could identify patterns within cluster structures to create new materials with specific design characteristics. And another potential application can be in finance, like financial market. They exhibit complicated dependencies and correlation among assets, and the traders often rely on complex machine learning algorithms to forecast prices and risk. Here, CAN could facilitate financial risk management by analyzing historical data containing many variables to develop forecasts taking into account underlying structure and relations between the assets. So overall, this CAN represents a promising advancement in machine learning, offering improved accuracy and interpretability over the traditional multilayer perceptrons, particularly in the situations requiring compositionality handling. Thank you.